Hello and welcome to part 2 of the Microtesting Workshop. First, let's quickly review what we covered in part 1. We looked at the attributes of good microtests by applying the test first acronym: fast, isolated, repeatable, self-verifying, and timely. We examined the 3 A's of microtests: arrange, act, and assert. We explored how to ensure that each microtest is focused on just one particular aspect of the functionality. We identified code smells that are unique to microtests. And finally, we had an overview of some test doubles, stubs, fakes, and mocks that allow us to handle dependencies and legacy code much more easily. In this part of the workshop, we're going to get our hands dirty and explore how to apply microtesting to real-world situations. We'll discuss what you need to test and how to make production code much more testable. So what exactly do you need to test? Ron Jeffries was a member of the first extreme programming team at Chrysler in the late 1990s and was the original Agile coach. His advice is quite simple and straightforward: test anything that could possibly break. Doesn't that mean, though, that you'll have to write a crazy number of tests for any non-trivial system? Well, yes it does, but if you recall the guidance from part 1 to write small, focused tests, then the effort that goes into writing those tests isn't as extensive as you may think. Does that advice to test anything that could possibly break mean that we have to test every single line of code and have 100% test coverage? Well, let's consider this getter method, getStation. Is there anything in that code that could break? In other words, not execute the way we'd expect it to? No. There isn't any processing, there are no conditional statements, it's simply returning a value. The only possible reason for this code to have a test is to ensure that both the setter and getter are working with the same value. I say that because a developer who once told me that you shouldn't test these methods made a copy-paste error and had a getter method returning the wrong value. However, in general I wouldn't bother. Additionally, if you're using an IDE such as Eclipse, IntelliJ, or NetBeans, or a modern code editor like Visual Studio Code, you could generate setters and getters for fields in a class without having to worry about that dreaded copy-paste error. What about this method? It's certainly more complex than a getter, so does it require a test to verify that it works as expected? No, generally it doesn't. This is what's called a composed method. It consists solely of calls to other methods without any processing or conditional logic of its own. If each of the methods it calls are adequately tested, we can reasonably assume that this method won't break. How about this example? It's more complex than either the composed method or getter examples. Yes, this code could break in the sense that there are multiple execution paths depending on the value passed to it. We would definitely want to write tests to verify that it has been coded correctly. For this example then, let's consider what we would have to verify. There are 5 execution paths through this method, and to cover them all, here are the scenarios for the tests. What should be returned when the string is empty? What should be returned when the string is null? What should the count be when the string doesn't contain any whitespace characters? What should the count be when there's one whitespace character? What should the count be when there's more than one whitespace character? And what should the count be when there are whitespace characters other than space? Here are those scenarios coded as microtests. Sometimes it can be helpful to list out the conditions and values that need to be tested like this. Your friendly QA people can also help by identifying edge cases that a developer might not consider. I recommend actively engaging with them to help improve your testing. Here's another example, also with 5 execution paths. What scenarios should we consider testing for this method? Ship2 is null, ship2 is a valid object, ship2 with an order type ID of null, and with a valid order type ID, ship2 with a price list ID of null, and with a valid price list ID, ship2 with a shipfrom org ID of null, and with a valid shipfrom org ID. And here are the tests representing 2 of those scenarios. So does this mean that you should stop all new work until you can write microtests for all your existing code? While that would be nice, it's most likely not feasible from a business perspective. To get existing code under test, the recommended approach is to write tests when you're changing anything or adding any new code. With a code base of any non-trivial size, though, this won't be an easy task. Code written without microtests will almost always have significant hard dependencies that are difficult to break, and likely will be structured in ways that make testing onerous. We talked about test doubles in part 1 of the series, and they will indeed come into play. But first, let's look at what makes code more easily tested. Not surprisingly, testable code looks an awful lot like well-factored object-oriented code. Small focused methods and small focused classes means exactly the same thing as highly cohesive code, and dependency isolation means the same as loosely coupled code. These are key aspects of object-oriented design. Also, to be able to make existing code more amenable to testing, you may have to perform some remedial refactoring prior to writing any tests. Why do we care so much about testable code? If you've been around software development for any length of time, you've likely encountered code that was just a mess. It worked most of the time, you'd think, but no one wanted to change it in case it broke something. When push comes to shove, though, you have to add that small change. You hold your nose, you make the change, manually test, and then hope you didn't break anything else. This video shows what happens when you use an approach like that. The C function in this video began its life as 300 lines of code roughly 10 years before this video was taken. In the state you see in this video, over 3,100 lines, that code had a cyclomatic complexity of 512, meaning that there were 512 possible execution paths through it. Because of the number of combinations and permutations of state required to test those execution paths, it simply isn't possible that the function has been completely tested. In fact, it's quite likely that parts of the function have never been tested. Shortly after this video was taken, that function was determined to be the root cause of a high-severity production issue that affected customer installations. Small classes and methods are, by their nature, easier to test. Smaller classes generally correspond with fewer dependencies. Smaller methods generally correspond with easier setup for any microtests exercising those methods. Classes should also have a single responsibility only, as should the methods within the class. Again, this is good object-oriented design, with the immensely beneficial side effect of making the code easier to test. Which of these examples do you think would be easier to test? The single large method on the left, or the collection of small methods on the right? While there are more methods in the sample on the right, the required setup and handling of dependencies is trivial compared to the sample on the left. The sample on the left also contains a network call to an external service, which adds other issues such as the slow test smell we discussed in part 1 of this series. We'll come back to this example shortly when we talk about remedial refactoring. One of the key tenets of good object-oriented design is to minimize dependencies on other classes. Often, though, this advice falls into the same category as code should be highly cohesive and loosely coupled. It sounds great, but we don't necessarily know how to do it because we don't have good concrete examples. Well, one qualitative tool we can use to determine if a class is loosely coupled, meaning its dependencies have been minimized, is by how easy it is to write microtests for the code in the class. Code that has few dependencies is naturally easier to test. To help isolate a class from dependencies, a common approach is to provide the means to have dependencies passed in using either a constructor or a setter method. This can eliminate hard dependencies created when you instantiate a dependency internally. As for singleton classes, they may seem to make code easier to use, but they create dependencies that make testing much more difficult. This sample method looks like it follows our advice to be small and focused, and to be fair, it is. However, it has a hard dependency created by instantiating the order summary service in the method, and another by hard-coding the order status list to be used by findOrdersByStatus. To write microtests for this method, we have to account for not just our class under test, but also the order summary service that it instantiates. It may, in turn, have dependencies on its own, in this case likely a database call. Similarly, since the list of statuses is hard-coded, we would have to ensure that not only can the test connect to the database, but also that the data already exist for those statuses so that we can verify the functionality. So how can we rework this code to minimize the dependencies and make it more testable? First, remember from test doubles in part 1 that interfaces are our friends when it comes to microtesting. So to start with, we can hide the order summary service behind an interface. Then we can move the concrete implementation that we already have into a class that implements the new interface. Now our client code has no dependency whatsoever on the concrete implementation of order summary service, nor does it have any hard-coded statuses. We can leverage what we've learned about test doubles to provide our own implementation that significantly simplifies our microtests. Here's the resulting test double, in this case a fake, that we've used to create for the purposes of our tests using the order summary service interface. We've substituted our own implementation of the order summary service interface's methods, and we were able to completely tailor the results from findOrdersByStatus to suit our needs for any tests using this class. To our production code, though, this test double looks like any other order summary service implementation. In summary, using Java interfaces is an essential approach to reducing the dependencies in code that's difficult to test. Singleton classes deserve a special mention in this workshop. Pictured here is Ralph Johnson in a 2015 presentation I attended in Chicago. Ralph is one of the 4 co-authors of the original book on design patterns. In this talk, he was discussing patterns in general, and had this slide especially for singletons. Singletons are effectively global variables and can create significant issues in object-oriented code. They increase coupling and dependencies in classes, they actually make components less reusable, and they make testing significantly more difficult. Ralph mentioned that there was some controversy among the book's authors regarding the inclusion of the singleton pattern. They eventually decided to include it, but he stated unequivocally, if we had known that singleton would have been abused so badly, we wouldn't have included it. Singleton, like any other programming construct, has its place. However, it should be used sparingly because of the adverse effect on testing in particular and object-oriented design in general. In part 1, I mentioned that we could use an interface to help break the dependencies that singletons create. Here's a relatively typical example that uses singleton classes for managing persistence in database transactions. There are 2 data access objects, DAOs, as well as a hibernate transaction that wraps everything. This save method is difficult to test as a result of the very hard dependencies on these singleton classes. First, we have to have hibernate running in order to obtain a transaction. Second, we need a connection to a database in order for our customer query to execute and for our order to be saved. Third, the customer table in the database must be populated with the correct data before the test runs. If all we wanted to test, for example, was the setOrderModified date was called with the current date, that's a ton of setup and teardown required, as well as a slow-running test because of the database call. I should note as well that there's actually a 4th singleton in this code that can complicate testing. Logging frameworks typically use a singleton pattern as static methods in their implementations. Again, this means that in order to test our code, we need to set up the logging framework. Often that isn't very difficult, but if your system sends log messages to a consolidated logging tool of some sort, then the setup becomes far too much for a microtest. Typically, it will suffice to have a separate logging configuration for tests that will either just write to standard error or standard out, rather than trying to completely replace the logging framework. So how can we refactor this code away from the difficult singleton dependencies? In part 1, while discussing test doubles, we examined fakes. I mentioned that there's a relatively simple approach to handle this issue by using fakes. Hide the singleton behind an interface in a simple class that implements essentially the same API as the singleton. So in this case, we pull out interfaces defining the methods that we require for our customer and order classes. We pass the troublesome hibernate session dependency in the constructor of our concrete production implementation. The resulting code without the hard dependencies looks like this. We pass the customer and order repositories in our constructor, but our class only sees an interface. As a result, the code in the save method no longer cares about the implementation of those classes. On the right is a sample test that creates two fakes for the customer repository and order repository. The test itself no longer has to concern itself with any Hibernate configuration, database connection, or pre-existing data in order to be executed. This simple approach, extracting an interface and faking, is immensely powerful in trying to wrestle with legacy code to get it under test. Here's another test to consider. If we wanted to verify that the save method returns the proper value when an exception is thrown, it's now quite simple to create a fake that generates an exception for us. That would have been next to impossible to do before this code was refactored to use interfaces rather than the hard dependencies it originally had. This example of how to deal with singletons used some relatively simple changes to make it easier to test what began as a 25-line method. But what about that monstrous 3100-line method we saw in the video? How can we possibly even begin to write microtests for that? While the video quality was quite low so the actual code couldn't be seen, you may have noticed that there were repeating blocks that appeared to be similar. In fact, almost all those blocks were identical and could have been extracted into a single method that would have been small enough to test on its own. Making changes like this is called remedial refactoring, and with legacy code we may need to perform some of that before we begin to write microtests. Again, leverage your tools. Modern IDEs have built-in refactorings that are extremely reliable. Extract that method. Change that variable or method name to make it more clear. Rename that class and extract an interface. Those small changes will pave the way for adding microtests much more easily. A common concern about extracting many small methods is that there will be adverse effects on memory usage and performance due to the overhead of calling these methods. While there are situations where that might be a legitimate concern, they're relatively few and far between. If you're concerned about the performance impact, profile the code before and after the changes to see the actual effects rather than just theorizing. It's quite possible that the Java compiler's optimizations will already eliminate any potential memory or CPU issues for you. So when dealing with a large chunk of legacy code, start by extracting one method and writing microtests for it. Then extract another method and do the same. Repeat the process until that original monster is gone, and you have a group of well-tested, small, focused methods. As an example, here's a rather large wall of code. Don't worry about the size of the font, you don't necessarily need to see individual lines of code. What's more important is to see how the code is structured. This is from a single method in a class that parses coded weather reports from a service on the internet. We've seen parts of this code before in part 1 when we introduced the extract and override technique as well as when using test doubles. But this example is a mess. If we wanted to write microtests which verified that the method was parsing the coded weather string properly, where would we start? Well, a hint comes from the diligent developers who touched this code before us. You may notice that there are comments at the start of each block of parsing code. It's not unusual to encounter these when looking at legacy code, and quite often these comments not only suggest where we can extract smaller methods, but they often suggest good names for the new methods as well. Using nothing but the comments as a guide and the built-in extract method refactoring, that massive method becomes this much simpler one. We also removed the section that printed the results and moved it to a class that uses this parser. The parser class's responsibility is to parse the weather report string, not print the results. Certainly there are other refactorings that could be performed to further simplify the code, but this is enough to start with. Now we have numerous smaller methods that can be tested individually. We can already test these without needing the dependency on making the external call to the weather service. That allows us to focus our tests on ensuring that the methods are parsing the weather report string properly. Even the longer parsing methods such as this one aren't too onerous to test, although again we could consider further refactorings to make this even simpler. With a little more refactoring, the tests become very straightforward and easy to write. Also note the use of concrete examples of the data to be parsed in these tests. Since this is sample code, the examples are by no means an exhaustive list of all possible combinations that need to be tested. However, using examples like this is a common approach when dealing with legacy code. If we know the code already works given the sample data, then we can use those samples to ensure that our changes haven't broken anything. Remember that wall of code with everything in a single method? After some remedial refactoring to get the code under test, and further refactoring with our microtests as a safety net, the whole class becomes much simpler, cleaner, more understandable, and easier to maintain. In this workshop, we've looked at what code should be tested. Essentially, you should test any code that performs computations or has branching logic, anything that could possibly break. When faced with legacy code, though, it makes more sense to add microtests only when adding new code or changing existing code. We also explored why it's critical for code to be testable and the attributes of testable code. Use small methods in small classes that are focused on a single responsibility. We want to reduce the dependencies in our code as much as possible and looked at how to achieve that through reasonably simple changes. And finally, we discussed remedial refactoring, how to make small, safe changes to our code that will allow us to write microtests much more easily. Here are some further resources on microtesting that will help you better understand and use the concepts we've explored. Thank you for watching.